First of all, I would like to thank Professor Onur Mutlu for the kind invitation to give this lecture. My objective today is to give a high-level overview of in-memory computing with an emphasis on memory devices and emerging applications. So I work for IBM Research. IBM Research is made up of around 3,000 researchers spread across the globe. It's a diverse group of computer scientists, mathematicians, electrical engineers, and physicists given a common mandate of figuring out what is next in computing. I belong to IBM Research Europe in the Zurich Research Laboratory. Some of you may have visited the facility. It was established in 1956 and happens to be the second oldest research lab of IBM. And here I manage a group where we investigate various aspects of in-memory computing, all the way from the physics of memory devices to the algorithmic and software-related aspects. So here is the outline of my lecture. First, I will briefly introduce in-memory computing. Then we will look at the primary constituent elements, namely the memory devices. We will look at the key computational primitives enabled by in-memory computing. So this is this first big chunk here. It's all about memory devices and the computational primitives. Thereafter, we will look at a range of applications, all the way from exploiting non-volatile binary storage and scientific computing to stochastic computing. So this is the second big chunk of the lecture. And finally, we will discuss some of the more exotic research topics, and I would like to summarize the lecture. Right, so I'm sure that you have heard this already from Professor Onur Mutlu earlier in the course. If you look at a modern computing system, we see three key trends. So first of all, data access is a major bottleneck. Energy consumption is a key limiter. And the energy for data movement far exceeds the energy to compute. So this means that there is a significant incentive in performing computation in or near the memory. This broader paradigm is typically referred to as processing in memory, or PIM. In my view, PIM can further be subdivided into two: in-memory computing and near-memory computing. And I will try to clarify this distinction pretty soon. In this lecture, my focus will be solely on in-memory computing. So what is in-memory computing? So let's look at a conventional computing system shown here. Assume that there is data A stored in memory. You want to perform f of A operations. A is then read from the memory and brought to the processing unit. F of A is performed and stored back in memory. This leads in-memory computing, A is stored in a specialized memory array. Let's call it the computational memory. Now, the whole idea is by applying an appropriate control signal, we are able to compute f of A in place without the need to shuttle the data back and forth in that process. And how do we do that? This is achieved by exploiting in tandem the physical attributes of the memory devices, their array level organization, and the peripheral circuitry, as well as the control logic. Now, a key distinguishing feature of in-memory computing is that, let's say in contrast to near-memory computing, is that at no point during computation, the memory content is read back and processed at the granularity of a single memory element. So we are always collectively processing the information as opposed to reading each individual memory element and doing the processing at the periphery, like in the case of near-memory computing. So hope this distinction is fairly clear at this point. So why is in-memory computing interesting? As mentioned earlier, in-memory computing can reduce the movement of data. As you know, in modern computing systems, the cost of data movement far exceeds that of computation. Even at the relatively old 45 nanometer technology node, the cost to multiply two 8-bit numbers is 0.2 picojoules, whereas a DRAM access requires energy in the vicinity of a nanojoule. So even accessing on-chip SRAM is a couple of orders more energy consuming than the multiply operation. Now, the second reason is the ability to reduce computational time complexity. Much of this arises from the massive parallelism afforded by a dense array of millions of memory devices performing analog computation. It's also likely that by introducing physical coupling between the memory devices, we can further reduce the computational time complexity. Let's now look at the memory devices and computational primitives. So, naturally, memory is at the heart of in-memory computing. And it's essential to understand how we store information in memory devices. I know it is probably getting farther away from computer architecture, but it's instructive to get at least a high-level picture of the physics of information storage. So traditionally, we have been storing information in terms of charge on a capacitor. In the case of a DRAM, we have a capacitor in series with a transistor. And in the case of flash memory, we have a capacitor coupled to the gate of a transistor. The absence or presence of charge on the capacitor indicates different logical bits. Now, there is this emerging class of memory devices where information is stored in terms of differences in atomic arrangements or orientations of ferromagnetic metal layers. For example, one atomic configuration within a nanoscale volume of material corresponds to one logic state, and the other one corresponds to another logic state. Now, the difference in atomic arrangements can indeed be induced by applying electrical pulses and measured as a difference in resistance values. Hence, they are typically referred to as resistive memory or sometimes as memoristive devices. They are based on a range of physical phenomena from ionic drift to phase transitions. So in recent years, in-memory computing has been facilitated with both charge-based as well as resistance-based memory devices, but by exploiting different physical laws. Now, in the next few slides, we will dive deeper into some of the key computational primitives enabled by both charge-based as well as resistance-based memory devices. So first, let us look at the charge-based memory devices a bit more in detail. A 6-transistor or a 60 SRAM cell consists of 2 CMOS inverters connected back to back. The charge, as you can see here, denoted by these balls here, they're confined within the barriers formed by the field effect transistor channels and by gate insulators. This is rather leaky. The charge can leak out, and hence the stored charge retention is small, and an external power source, has to constantly replenish the lost charge. That is why SRAM is typically referred to as persistent memory. Now, if you lose external power, then we lose all information in no time. But SRAM has almost unlimited cycling endurance and sub-nanosecond read and write time. So it's the fastest memory out there. Now, a DRAM cell comprises a capacitor that serves as the storage node, which is now connected in series to the FET. So it's again the charge sitting here. Since the FET barrier is limited to the band gap of silicon, the charge can be retained only for a fraction of a second, typically tens of milliseconds, and this necessitates a periodic refresh. Now, the storage node of a flash memory cell is indeed connected, as we discussed earlier, is coupled to the gate of the FET, with a charge stored either on a conductive electrode surrounded by insulators or in discrete traps within a defective insulator layer. So this means that the charge is well preserved, is well protected, and hence it can be retained for a long period of time. But naturally, this also means that getting in and getting out the charge is going to be time consuming and costly, and this will have ramifications on the access time and the cycling endurance. You can see that the cycling endurance, a number of times the device can be switched from one state to the other, is substantial for DRAM or SRAM, and also the access times for flash is significantly worse compared to the other two. Right. So what we see is that we can implement a whole range of in-memory logic and arithmetic primitives using charge-based memory devices. First, we'll look at how we implement logical operations using DRAM. I just want to point out that if you look at the underlying physical law that enables computing using the physics of these devices, that is typically capacitive charge redistribution, right, when it comes to charge-based memory devices. So that kind of serves as the foundation for many of these computational primitives that we'll see. So here is an example of performing logical operations using DRAM. We are performing bitwise and OR functions. There are two memory cells here, so A and B. They are used to store the operands. Now the logic state of the third cell, we call this, which is denoted by cell, SEL, is set to 0 or 1, and this will dictate whether an AND or an OR operation is realized. So the essential idea is as follows, right? You have all these cells here, then you activate all these cells simultaneously. Now, because of the capacitive charge sharing, the bit line voltage now will be an average voltage across the three capacitors. So this is what you have at the end, right? Now, this bit line voltage is now sensed with a sense amplifier with a single decision threshold. So it will, if you cross the threshold, it will say is 1. If it is below the threshold, it will say it is 0. And this threshold has to be chosen appropriately. Now, what happens if V cell is 0, then you see that the net voltage levels will be lower, and hence an AND operation will be performed, right? So this is what happens when V cell is 0. But now if V cell is non-zero, then the net voltage levels will be higher, and hence you will be performing an OR operation. Of course, it all depends on how we select the reference voltage for the sense amplifier, but you get the idea. Right, so how about SRAMs? Can they also do logical operations? Indeed, yes. So there have been demonstrations of performing logical operations using SRAM cells as well. And since SRAM cells do not contain a built-in capacitor like DRAM, the parasitic bitline capacitance is used instead to enable in-memory logical operations. So I'll show how bitwise AND and NOR functions are realized using an array of two SRAM cells holding the operands. So here again, you have A and B holding the operands. And here again, the core idea is a simultaneous activation of word lines, right? Now, in an SRAM, we don't have just BL, the bit line, but we also have a bit line bar, 2 lines. And it can be shown that by sensing the bit line voltage, we can realize the AND operation. And by sensing the bit line bar voltage, we can realize the NOR operation. So how do you do that? So you pre-charge the bit line and bit line bar to the supply voltage. Now, after deactivation of the pre-charge signal, both the word lines are activated simultaneously. Now, both bitline and bitline bar are discharged at different rates that depend now on the data stored in the bit cell. So that is a key here. So the data that is stored here will determine how the charge is discharged, right? And that is a key trick here. Now, when the two activated SRAM cells in this column are both ones, like if A and B are both ones, then VBL will be closer to the supply voltage. And in that case, if you look at the bit line voltage, you will realize your AND operation. Now, in the same vein, if you are monitoring the bit line bar voltage, right, it would now be detecting, or it will be implementing the NOR logical operation. So that's the trick here. So this is how you implement logical operations in SRAM. So in both cases, you can realize a bunch of logical operations, and then you can build up based on that. You can do bulk bitwise operations and implement other computational primitives using them as the basis. So besides logical operations, we can also perform arithmetic operations based on charge-based storage devices. SRAM arrays in conjunction with capacitors organized in a crossbar configuration as shown here have recently been shown to perform analog matrix vector multiply operations. Suppose we want to perform this AX equal to B with a binary A matrix. Then what we do is we store the elements of the A matrix in these SRAM cells shown here, right? So these 4 SRAM cells will store the values corresponding to that binary A matrix. Right, the matrix vector multiply operation itself is now involved 3 distinct steps. So in the first step, the inputs the xi, right, is now are provided per row that charges the capacitors on that row to a value proportional to that, right? So these inputs can be analog. So you apply them over here to charge these capacitors. Now, in step 2, the capacitors that are associated with the SRAM elements storing the zeros are discharged. So you take them out of play. You discharge that charge from the capacitor. And in step 3, the capacitors are shorted along the columns, performing this charge sharing operation so that the final voltage developed along the columns is equivalent to or is proportional to the result that you're looking for, which is the BI. So that's the idea here. So again, as you can see in this particular example, A matrix is binary, X is analog, or it's a floating point or whatever it is, and B is analog, right? Now, this approach is gaining a lot of traction these days. There are several extensions of this concept being developed, with a lot of papers appearing in top circuits venues, including this recent one from our group. So flash memory can also be used to perform matrix vector multiply operations when organized in a crossbar configurations. Just shown here again, you can see four flash memory cells organized in this particular manner. So here again, here on the other hand, the matrix elements themselves can be analog, and they are stored in terms of the charge on the floating gate of the flash memory cells. This will in turn determine the threshold voltage of the transistor. And now the current flowing through the transistor is a function of the threshold voltage, among other things. Now, based on the binary input vector in this case, we modulate the gate voltage, right? So this goes here and here, proportional to the desired, so we modulate the gate voltage, and because of that, the net current will now be proportional to the desired B vector that you're looking for. So these similar concepts are pursued by quite a few startups. In fact, one of the more prominent ones, Mythic, recently announced their first product based on 40 nanometer CMOS technology. There's a lot of stuff that you can read up on this concept. Is again getting a lot of traction. Now let us look at resistance-based memory devices in a bit more detail. The history of resistive RAM can be traced back to the 1960s. Resistive RAM refers to a device structure consisting of a metal insulator metal stack, as shown here. The resistive switching process typically involves the creation and rupture of conductive filaments, localized concentration of defects. A low resistance state corresponds to conductive filaments bridging the two metal layers. PCM is a bulk switching resistive memory, which depends on the reversible phase transition of certain types of materials. Both PCM and resistive RAM have a relatively large resistance window and moderate cycling endurance. You can see that the resistance range is quite large, whereas the endurance is not that impressive. Now, a relative newcomer, the MRAM, magnetoresistive random access memory, consists of a magnetic tunnel junction (MTJ) structure with two ferromagnetic metal layers, the free and the pin layers. Depending on whether the two ferromagnetic polarizations are parallel or anti-parallel, the low resistance state and high resistance states are obtained due to the tunnel magnetoresistance effect. In MRAM, you see that the resistance range is actually rather small, but the endurance could be significantly higher than PCM and resistive RAM. Right. Now, so how do we perform logical operations using resistance-based memory devices? So if you look at conventional CMOS logic, the voltage serves as a single logic state variable. The input signal is a voltage signal. It's processed as a voltage signal and is output as a voltage signal, as you can see here in this diagram. The CMOS gates regenerate this state variable during computation. Now, how about using the resistance state of memory state devices an additional state variable? For example, a high resistance state indicates say logic 0, and a low resistance state indicates logic 1. We need just binary storage capability for this. So we just need a memory device which can switch between these two high resistance and low resistance states. We can toggle these states by applying suitable voltage signals. And this enables us to implement several basic logic operations based on the interaction between the voltage and resistance state variables. So that's seemingly integrating memory and processing, and you will see some examples pretty soon. So there are several logic families proposed to do this particular thing. Now, one particularly interesting characteristic of certain memristive logic families is statefulness, where the Boolean variable is represented solely in terms of the resistance state. So the whole circuit resistance is only logic state variable. It was first introduced by Stan Williams at Hewlett-Packard in 2010 by showing how we could implement this so-called material implication logic. Now, another elegant realization of the so-called stateful logic is magic. It's another approach that was presented that realizes the NOR logic operation in this case. It's not a material implication, but it is a NOR logic. Now, as you can see in the top here, both the operands and the results are stored in terms of the resistance state variables. So these are the two operands here, and this is the result here. Okay. Now, how do we do it? So you first initialize the result device to logic 1, which is a low resistance state, as we discussed earlier. And now, subsequently, what you do is you apply a voltage pulse with an amplitude larger than twice that of the V reset to both operands. Both operands devices receive it. Now, what you see is that if either of the operand device is in logic state 1, then at least half of that voltage will drop across the result logic state device, and that will switch now from 1 to 0. It will go from the low resistance state to the high resistance state. But in the case where both the operands are 0, this voltage cannot drop because there's a very high resistance state here. So then this will remain at 1. So essentially what you have now realized is that you have realized this NOR operation, but as you can see, all the logic state variables are represented in terms of the resistance states of the memristive devices. So it's a very simple, elegant way of implementing stateful logic. But there is a significant drawback for stateful logic. That is that you need to repeatedly program the memristive devices. And given the limited cycling endurance and the high energetic cost associated with programming these devices, this is actually a key drawback for stateful logic. So because of this, there is this renewed focus on non-stateful logic where both resistance and voltage state variables coexist. So for example, you could store the data in terms of resistance logic state variables, right? You can have devices such as this where the resistance state of these devices now indicate the data, whereas the logical operations themselves are implemented in the periphery, and then it will be outputting logic state variables in terms of the voltage, right? So the logic operations themselves are implemented by virtue of this peripheral circuitry, and only read operations are employed. And this is really nice. So for example, by simultaneously sensing multiple memristive devices, like in this case, connected to the same sense amplifier, but with a varying threshold current, we can realize AND and OR operations. So you could just this is a nice illustration of how that works. So just having two different threshold voltages, you can perform either an OR operation or an AND operation, and we'll see more about this in terms of an application later on. Right, so moving on to arithmetic operations now. One operation that can be realized rather easily using resistive memory devices is that of matrix vector multiplication. So here again, if you want to perform the operation AX equal to B, then what you do is the devices have to be arranged in a crossbar configuration as shown here. So these are the devices. The 4 devices now store the weights. So for AX B, then we could map A to the conductance values of these devices. The X values should be now linearly mapped to the read voltages applied here. So these ones would be the corresponding to the X values. And then what you see is that the resulting current along each column will now be proportional to the result B. As we will show in greater details later on using phase change memory, the property of device that is used to enable this is the analog storage capability. Just the fact that these memory-stive devices can achieve analog conductance values, and also the Kirchhoff's circuit laws, the Ohm's law, and the Kirchhoff's current summation law. Now, if you reverse now the process and apply the read voltage along the columns and measure the current along the rows, then we can also perform multiplication with the transpose of the matrix, another key computational primitive in a whole bunch of applications. So it's a very elegant way of performing very fast matrix vector multiply operation. In this case, reducing the computational time complexity, for example. So, in the next few slides, I would focus which is a prototypical resistance-based memory device. Phase change memory is based on this property of certain compounds of germanium, antimony, and tellurium, where they have drastically different electrical and optical characteristics depending on their atomic arrangement. For example, in the disordered amorphous phase, they have very high resistivity, and the ordered crystalline phase, they have very low resistivity. Now, if we sandwich a tiny volume of this material between two metal electrodes, then we can make a memory device as shown here. Now, how do we do that? So by applying a voltage pulse and subsequent Joule heating, the material can be reversibly switched from the crystalline phase to the amorphous phase. And depending on the phase configuration, the device will have different resistance values, and this can be deciphered by biasing with a small amplitude read voltage. So phase change memory is by no means a new technology. It was actually pioneered by Stan Oshinsky in the 1960s. So Stan was his prolific inventor, and he had patented a wide range of device concepts based on phase change materials. In fact, even if phase change memory's chip was fabricated and published as early as 1970s by Ron, Neil, Gordon Moore, and so on. So this chip had a capacity of just 256 bits, but it was not the only issue. And if you look at the specs, just to set a device from 0 to 1, dictated by how fast we can crystallize the material, that required 10 milliseconds. And to flip a 1 to 0, dictated by how much power we need to pump in to melt the material, it needed 200 milliamps. So naturally, it was not very competitive. And in the coming decades, much of the attention went into flash memory and so on. So in the meantime, though, some parallel developments were taking place. Phase change materials, even though not very successful in the electronic memory domain, found a lot of commercial success in the optical recording domain. This meant that a lot of research went into fast crystallizing phase change materials, and now you could crystallize phase change materials in the order of hundreds of nanoseconds to tens of milliseconds. There was also significant advances taking place in the semiconductor manufacturing domain. Moore's law was running its course. We could fabricate much smaller devices. This meant we can make PCM devices with nanoscale volumes of material that we only require, say, hundreds of microamps to melt the material instead of hundreds of milliamps. So hence around the 2000 timeframe, there was a renewed interest in phase change memory, with several companies, including IBM, jumping on the PCM bandwagon again. So there's a lot of debate from the very early days as to where PCM could fit in the memory storage hierarchy. At IBM, we always believed that storage class memory that sits between the fast volatile DRAM, so this is the storage class memory region here, and the non-volatile flash hard disk drive is a sweet spot for PCM. So if you look at all the relevant specs, PCM was bang in the middle of DRAM and flash. In fact, if you look at the recent commercialization of phase change memory as storage class memory by Intel and Micron, this kind of validates this initial belief that we had that storage class memory is probably where PCM is best suitable for. So in this talk, I will mostly focus on phase change memory for in-memory computing and not for storage or memory. And why is PCM the front runner for in-memory computing is twofold. First of all, it is successfully commercialized, so people know this works and we can manufacture them. The second reason is that it's one of the few emerging memory technologies where the device physics is very well understood. So my own group was personally invested in this effort for over a decade now. So each PCM device is indeed an intricate feedback interconnection of electrical, thermal, and structural dynamics. And over the years, we have figured out how this all works together, and we have a pretty good handle as to how this device works. So that's also another big reason for us to work on PCM for in-memory computing. So what are the key attributes of phase change memory that facilitate in-memory computing? The first attribute is that the devices can be switched back and forth billions of times, and we can have two non-volatile states. But if you look at a large number of devices in an array, as shown here, the two states may have a broad distribution. For example, this is the distribution corresponding to the set state or the low resistance state. You see that it's rather broad, right? But nevertheless, we still have non-volatile binary storage capability, but with a wide distribution of set and reset conductance values. So what is the second key attribute? So PCM is not just a binary storage device, right? It is also, by applying suitable electrical pulses, we can achieve intermediate phase configurations where we modulate the size of the amorphous regions shown here. So these are, you can kind of create like a mix of amorphous and crystalline phase configurations. And in this manner, we can achieve a continuum of resistance. But on the other hand, there are a lot of non-idealities such as temporal conductance drift and noise, which will be there. So you can achieve a certain analog conductance value, but there's a lot of conductance variations around it. So essentially, we have analog storage capability, but with significant conductance variations. So as we saw earlier, we can exploit the analog storage capability of resistive memory devices, such as phase change memory, to perform matrix vector multiply operations. So the example that we showed earlier. So in this case, it's shown again in terms of how you would do it with the phase change memory devices. We also said that we can perform this multiplication with the transpose of the matrix, and the attribute of analog storage capability is what we exploit together with Kirchhoff's circuit laws, the Ohm's law and the Kirchhoff's current summation law. Now, due to the conductance variations that we talked about, the precision associated with this operation is not particularly high. So it's true that we get this tremendous improvement in computation time complexity, but on the other hand, you take a hit in terms of the computational precision. So for example, very often in our lab. Suppose we code A in a 256 by 256 Gaussian matrix, coded in, or we code this matrix in a PCM chip, and if we perform the matrix vector multiply operations, what is plotted here is the estimated BI hat values against the exact BI hat, and if everything goes well, it has to be a perfect 45-degree line, but you see that there is quite a bit of variations around that, right? So what is shown here is blue is what you get from the PCM chip, and so there is this reduced precision that we have, and at this point, if you look at these devices, it's kind of comparable to a 4-bit fixed point memory. Now, there is one more attribute that we can exploit for in-memory computing, and that is the cumulative behavior. So if we start from a fully amorphous reset state, now by applying a sequence of crystallizing pulses of the same amplitude, we can progressively crystallize and achieve lower resistance values or higher conductance values. So this behavior is though often highly nonlinear, as you can see here, if you plot against conductance versus number of pulses, and it suffers from significant intra-device stochasticity. Exhibits a different accumulative behavior at multiple runs. So essentially, we have a non-volatile integrator, but nonlinear and stochastic. So these three attributes, namely the non-volatile binary storage, analog storage, and accumulative behavior, serve as the basis for in-memory computing using phase change memory. So note that any other memory technology that exhibits one or more of these three attributes is also a viable candidate for in-memory computing. So there's not by any means limited to phase change memory, but these are the key attributes that we are looking for if you want to see if you can do in-memory computing using a certain memory device. This part of the lecture, we will look a bit deeper into the applications that are enabled by in-memory computing. So you can see if you just look at, there's something that we compiled earlier this year where we looked at all the applications that are out there which are making use of in-memory computing. And what you see is that the applications have varying degrees of computational complexity and the data motion, right? And requirements in data motion. And both of which, as we saw earlier, can be addressed by in-memory computing. Now, the application areas themselves can be broadly classified in accordance with the computational precision that is required. So on one end of the spectrum, you have scientific computing, where we require very high precision, while on the other hand, we have the stochastic computing, which actually relies on imprecision. And in the middle, you have the signal processing, machine learning, optimization kind of domains, which, in my opinion, in-memory computing is particularly well suited for because it doesn't require such high precision, but you can also have significant gains in both computational complexity as well as requirements and data motion. Right. So in the beginning, first we will look at the applications that exploit non-volatile binary storage, in-memory database query, and in-memory hyperdimensional computing. So database query is one of those applications involving a high percentage of logical operations. When performing queries on large databases, one of the main challenges is to retrieve the stored data and to bring it to the processor that will execute the query. So here is shown a simple example data set with 8 entries representing information of newly discovered stars. Each entry has 3 characteristics, that is distance, size, and the year in which the star was discovered. And now the right that represents the bitmap representation of the same data set, where the 3 characteristics are encoded into 7 rows of zeros and ones. Each column, for example, say column A, is an entry, while each row is a characteristic. For example, a star with distance larger than 40 is defined as far and otherwise as near. Now, with this bitmap representation, we can carry out queries by performing bitwise logical operations as shown by these examples here. So we can ask questions like which star is far or large, or which star is near and medium, and then all of them will turn out to be just bulk bitwise logical operations. Now, so how about, so what is in-memory database query? So how about storing the databases in dense arrays of non-volatile memoristic devices as shown here, and executing the queries directly in memory by employing the in-memory logic operations that we talked about earlier. So for example, so we have a database here. Now the operands can be stored in terms of the conductance states of memoristic devices. So you can store them in this particular manner, organized in a crossbar configuration. Now, to perform logical operations, multiple rows are biased simultaneously, and the resulting current is sensed per column using variable reference sense amplifiers, like again what we saw when we discussed the non-stateful logic. According to the input query, a controller provides the appropriate reference current. So these are the ones which changes depending on whether it's and or logical operations. Thus, we are kind of obviating the need to move the operands into an external processing unit to perform these database query operations. So this concept was recently demonstrated in our lab in a PCM array that we fabricated entirely in Zurich. So there's just a 10 by 10 array of PCM devices. Now this array holds again a simple database related to IBM's research labs, various attributes of the research labs. Then we experimentally queried this array to obtain answers to questions like, which lab received the Turing Award or the Kavli Prize, for example, right? And then it pops up, Almaden, Yorktown, and Zurich. So, you can just probe this query and, this database without having to move data into a processing unit. So that's all nice, right? It's a nice simple demonstration of how you can do in-memory database query, but real world database queries consist of a multitude of sub-queries with associated logical operations rather than a single query. So it's not always just one query, but it's a compound query. So solving such a query in the previously demonstrated manner could yield a very inefficient system. The main challenge being the requirement to have this additional memory unit for temporary storage of intermediate logical results. So we also need to fetch them for further processing along with the next set of logical outputs. So a more attractive option is to perform a cascaded query, both in memory and near memory simultaneously. So this is possible because these compound queries that I talked about, the real world queries, they can be expressed as a sum of products or the product of sums, where the sum and product operators corresponds to the or and operations respectively. But just by having this, the near and in-memory computing working in a nice complementary manner, we can design very efficient systems to take care of these kind of compound real-world queries. And again, we showed one of these examples in that paper that we published. So so just want to point out that this, database query is a very interesting application for this in-memory logic primitive that we talked about. So there's one more interesting computational primitive, an application which relies on this non-volatile binary storage capability, and that is hyperdimensional computing. So what is hyperdimensional computing? Hyperdimensional computing is this emerging computational framework that takes inspiration from the attributes of the neuronal circuits. As you know, our brains are massive entities with billions, hundreds of billions of neurons and hundreds of trillions of synapses. So this is the basis that hyperdimensional computing takes to form this form of computational paradigm. Now, the other interesting attribute that you see in the brain circuits is its remarkable robustness to failures and imperfections. So the question is as follows. So what if we compute with very high dimensional vectors instead of, say, the 32 or 64-bit words that we typically use in our computing systems? And also, why not take away the notion of MSB or LSB, which kind of reduces the robustness of the arithmetic that we do, right? Because if you make an error in the MSB, then the implications are much larger than when you do something in LSB. So why not have all the bits have equal significance? Another very nice property of these high dimensional vectors is that when we randomly draw them, they are nearly orthogonal to each other. So if you look at the Hamming distance of two randomly drawn 10,000 dimensional vector, then almost invariably they're almost orthogonal, right? And what can be shown is that by manipulating such high dimensional vectors, we can efficiently realize certain machine learning tasks. So here is an example of classifying European languages. Assume that we want to know which language a certain text belongs to. So for this, first we need to find a prototype hypervector corresponding to each language. And this process of creating this prototype hypervector is known as encoding, and this is how encoding works. So let's say we have one random hypervector corresponding to each letter of the alphabet, say A to Z in space as shown here. These hypervectors are collectively referred to as item memory. So we call it the item memory. Now suppose a phrase is input into the encoder, in this case ich bin, we can perform trigram encoding by taking 3 letters at a time. So we look at the first 3 letters, for example. So pick the first 3 letters. So pick the first letters hypervector. Then, since it's appearing first, you permute it twice. And pick the second letter, C. Then you permute it once. And pick the third letters hypervector and leave it as it is. Right? So we have done that. Now you perform a binding operation, which is essentially an XOR operation. So you bind them together. So that is now. So we do this binding operation for each trigram. So you keep moving. You see, you create the next trigram, next trigram, next trigram, and the next one, right? So you create all these trigrams. You create the corresponding hypervectors corresponding to the trigram, and after that, then finally you do this so-called bundling operation, whereby you add up the hypervectors and then you threshold the sum to obtain another binary hypervector. So this hypervector condenses the information contained in the phrase ich bin. So that's quite cool, right? So you start with this fixed random item memory, and then now you can create a hypervector corresponding to this phrase that went into that. Now let's extend it. So we could extend this encoding process now on a large ream of text from this language, right? So you could read a book, or you can have kilobytes of text and feed it through the encoder. So the encoder churns through all this data, and thereafter it produces a single hypervector after doing this whole process, which now in this case, since it's German, we would refer to as the German prototype vector. Now, by reading like a French book or a Greek book or whatnot, you can create similar prototype hypervectors for other languages. Now, suppose we want to know which language, suppose we want to know the language of an unknown text. All you have to do is to take that sentence, feed it through the encoder again. So you do the encoding process, and this time you obtain what you call a query hypervector, right? Now, by performing a simple associative memory search between the query hypervector and this 21 language profile hypervectors that you created, we can decipher which language that unknown text corresponds to. So all you have to do is to find out the distance between the query hypervector and the prototype hypervectors that we obtained during the training process. It's pretty cool. Now, so where does in-memory computing come into play in all of this? So one thing that you immediately notice when you look at this hyperdimensional computing system is that whether it is an encoding process where you find out the prototype hypervectors, or the associative memory search, whether you look for similarity between the query hypervector and the associative memory, HD computing mostly involves manipulation and comparison of high-dimensional vectors, right? Very simple operations on large vectors. So this is particularly well suited for in-memory computing. And also another point to note is that HD computing is remarkably robust to computational errors. So it's again another advantage of having in-memory computing there. So you could do both the encoding as well as associative memory search all in memory. Now the item memory for encoding and the prototype hypervectors for associative memory search can be stored in resistive memory devices as shown here. And via in-memory computing, we can implement all the key operations here. So recently yes, this is what I mentioned here. So recently we showed experimentally that we can sustain minimal accuracy loss when we implement hyperdimensional computing using phase-change memory devices and gain significant system level performance. So this is really a really fascinating domain, I think, for in-memory computing, and another application area where we are just using the binary non-volatile storage capability of MemoryST devices in this case to implement a very interesting machine learning task.
So here we demonstrate an example of language recognition application developed based on our experimental PCM platform. So we use hyperdimensional computing to determine the language of a query sentence written using the Latin alphabet. First, we enter the query sentence through this interface, and a part of the PCM array which is pre-programmed with the hypervectors of the letters in the Latin alphabet is used to compute a query hypervector for the query sentence. And now this hypervector is compared against 22 different potential European language profile hypervectors stored in another part of the PCM array, and the resulting language, which is the highest similarity, is finally returned to the host computer and displayed on the screen as you can see here.
Now let's look at scientific computing. Scientific computing applications employ a significant number of linear algebra computational kernels. Hence, in-memory computing, in particular the matrix vector multiplier primitive, can be very useful in this space. However, these applications typically require very high numerical precision. So one approach to remedy this problem is the use of bit slicing. So by slicing the matrix elements and inputs into tinier slices and then combining the results in a peripheral digital circuitry, we can improve the overall numerical accuracy. This is a very interesting approach, and you can read this particular paper which appeared in HPCA to know more about how you can use bit slicing to improve the computational precision or numerical precision for scientific computing. Now, another elegant solution is mixed precision in memory computing, where we combine potentially imprecise in-memory computing with higher precision digital compute to solve certain tasks. So since a big chunk of the compute is still done using in-memory computing, the overall system level performance would be quite good. So this is an approach which is referred to as the mixed precision in-memory computing. This was proposed by us a couple of years back. So let's look at how this mixed precision in-memory computing works with an example of mixed precision linear solver. So this is a very practical application that arises quite often in scientific computing. So the linear solvers, like solving systems of linear equations. So if Ax equal to B, we need to find out what X is. And how you typically go about when A matrices are very large is through iterative solvers. So you start with an initial solution, let's say X equal to 0, and then we update it iteratively based on a low precision error correction term, which we denote by Z. Now, the error correction term is computed in turn by solving another linear equation, Az equal to R, with an inexact solver, linear solver, using the residual R, which is B minus Ax. And this is the thing which has to be computed in higher precision. Now, the matrix multiply operations which are involved in this inner solver are performed using in-memory computing in an inexact manner. So we keep on running this algorithm, it's iterative, until the norm of the residual falls to a certain tolerance. So as you can see, the key idea of this approach is simple, right? So as long as we have a very good high precision feedback on the residual, then we can afford to make inexact updates, and these inexact updates can be computed using a very low precision in-memory compute engine. So as long as you have the residual compute in high precision, then you don't care if your updates are imprecise, and you can still have the algorithm converge to the right solution. It's a very interesting approach. And so this is the experimental demonstration of that. So to experimentally demonstrate this, we used model covariance matrices. And these model covariance matrices, they are kind of unique. I mean, they exhibit this decaying behavior that kind of simulates the decreasing correlation of features away from the main diagonal. They appear quite often in a range of applications the domain of HPC. Now, the matrix multiplications in a solver are all performed using phase change memory devices. And now what is shown here is basically the error plotted against the number of iterations. And what you see that as the iterations go along, your error keeps on reducing. And this is not kind of limited by the computational precision afforded by in-memory computing. So we can get arbitrarily high precision even though the inner solver is working on a very reduced precision engine. So you'll also notice that we'll have significantly less digital matrix vector multiply operations in the mixed precision approach compared to the full digital approach. So we did a thorough end-to-end system level performance analysis, and we found that we can have significant savings in both the speed up as well as the energy efficiency through this mixed precision in-memory computing approach. So let's now move on to a different set of applications. So as you saw, in mixed precision memory computing is very attractive for scientific computing where you need very high precision. But it would be nice to have applications where we can do almost all the computations in the in-memory computing domain. And that's where signal processing and optimization come in. Because there are numerous applications in this domain where approximate solutions can be considered acceptable, and the bulk of the computation could thus be performed in in-memory computing. So one of them is combinatorial optimization. So that is the process of searching for the maxima or minima of an objective function whose domain is discrete but has large configuration space. So to address these computationally intensive, typically NP-hard problems, simulated annealing inspired approaches such as the massively parallel Boltzmann machines and Hopfield networks have been proposed. The basic idea is to compute the inner products, the fundamental building blocks in place via in-memory computing, just very similar to what we did with the linear algebra problems. But an interesting additional prospect here is to utilize the device noise as an explicit source of noise to force the network to continuously explore the solution space. So you can kind of constructively use the device noise, the imprecision that arises due to IMC to achieve faster solutions. So this is a very nice paper which recently appeared in Nature Electronics where you could see how this is done to speed up combinatorial optimization problems. Another application domain in this area is compressed sensing. This is something that is particularly suited for in-memory computing, and I want to talk a little bit more about it going forward. So compressed sensing and recovery is one of those applications that could benefit immensely from in-memory. The objective behind compressed sensing is to acquire a large signal at sub-Nyquist sampling rate and subsequently reconstruct that signal accurately. So unlike most other compression schemes, sampling and compression are done simultaneously. The signal gets compressed as and when it is sampled. And it has widespread applications in the domains of medical imaging, security, camera sensors, etc. So the compressed measurements can be thought of as a mapping of a signal x of length n to a measurement vector y of length m, which is much less than n. If this process is linear, then it can be modeled by a m by n measurement matrix A. So it's just a matrix vector multiply operation from a high dimensional space of dimension n to a low dimensional space of n. And as you know, this measurement matrix now can be stored in a membristic crossbar array. And then we can perform this compression operation in order 1 time complexity as we have shown earlier. So it's a very simple way of compressing information. The recovery, though, is more challenging. So here we used the so-called approximate message passing algorithm for recovering the original signal because you're going from a lower dimensional signal to a higher dimensional signal, and this is always more challenging. But fortunately, so this algorithm works in a very beautiful manner. So it's again an iterative algorithm, and that involves, if you just look at it, it involves again matrix vector multiply operations, but now with not just with the measurement matrix, but also with the transpose of its matrix. And we know already from our previous discussions that both these operations can be implemented efficiently in in-memory computing. That means you can have the exact same measurement matrix that you coded for the reconstruction as well, just that you also start multiplying with the transpose of the matrix. Right, so what you see here is that if you do this operation, so in this way, we can use the same matrix, and the reconstruction complexity now reduces from order mn if you had implemented a conventional machine to order n, which is substantial because these m and n dimensions are very large. So here is an experimental illustration of compressed sensing recovery in the context of image compression. So we took a 128 by 128 pixel image, it was compressed by 50% and then recovered, whereby the measurement matrix elements are all encoded in PCM devices. So here again, the normalized mean square error is plotted against the number of iterations. And one thing that you immediately notice is that even though the in-memory compute operations are imprecise, it doesn't affect the convergence rate at all. So the convergence rate is independent of the position of the matrix vector multiplications, and the lack of precision is only resulting in a higher error flow compared to the floating point version. And often this kind of higher error flow is not detrimental for the application of sensing, right? As you can see even in this case where the image is compressed and decompressed, we don't see a real visible effect because of that. So that's one of the big advantages. So we also performed a thorough system level analysis to understand the gains of this. So we estimated a power reduction of almost 50x compared to using an optimized 4-bit FPGA matrix vector multiplier that delivers the same reconstruction accuracy at the same speed. So it's again another very fascinating application domain for in-memory computing. Let's now spend some time on deep learning. So deep learning is likely to be the most prominent driver for in-memory computing in the coming years. So I'd like to devote quite some time on this. So as you know, deep learning is an old idea, loosely inspired by the cortical architecture. A deep neural network consists of parallel layers of processing units known as neurons, interconnected by plastic synapses. Now, by tuning these synaptic weights, this network is able to perform certain cognitive tasks, such as figuring out which digit this is from looking at its pixel map. Now, to train such a network, there are essentially 3 steps. In the first step, an example from a large labeled data set is forward propagated through the network. And in the second step, the network response is compared with the label, and the resulting error is now back propagated. Both these propagation stages involves a sequence of matrix vector multiply operations. Now in the third step, the synaptic weights are updated to reduce the error, and this process is continued for thousands, if not for millions of training examples, and the whole process repeated several times. That's what we call epochs, and finally the network is said to be fully trained. Now, once trained, the network can perform inference or classification tasks on digits which it had not seen during training. This is the generalization, right? And is one of the surprises or miracles of machine learning. Right, so this relatively simple concept has revolutionized machine learning and is currently the mainstay of the AI portfolio for much of the IT industry. So the key reasons for this are the ability to collect amounts of data, these large amounts of data, as well as the immense computing power on offer. So hence, to a large extent, the success of deep learning owes a lot to the progress made by the semiconductor industry and the computer architects over the last decades. Now, it is well known that deep learning has a computational efficiency problem. It takes days, if not weeks, to train state-of-the-art neural networks, even with the most advanced computing hardware. The power consumption is highly undesirable, and by many accounts, it's unsustainable. As you know, deep learning is now employed across the stack, right, all the way from cloud computing servers to edge servers to the end devices. And in some cases, you may not have the compute resources on offer to have this kind of workloads run on them. So also there were very interesting articles recently in the MIT Technology Review where they pointed out, the impact of deep learning training on climate change, for example. So a key reason for this computational inefficiency, if you look at it, is the need to shuttle around millions of synaptic weights, right? And that is precisely where in-memory computing can be helpful, because that is what we try to address with in-memory computing, moving of data. So because of this, it's natural that there's a lot of research interest in applying in-memory computing for both deep learning training and inference. Here is just a snapshot of some of the recent efforts. Some of them are based on charge-based memory devices, such as SRAM and Flash, who can also do analog in-memory compute and in matrix vector multiply operations, as we saw earlier. And some of them are based on memory-resistive devices, such as resistive RAM and phase-change memory. And in this lecture, I will focus mostly on our work that we do using phase-change memory devices. So let's look at deep learning inference. In this case, we have a fully trained network. The synaptic weights are obtained by some training methodology, most likely in software. And these weights have to be mapped to an array of computational memory cores where resistive memory devices are organized in a crossbar configuration. And each core now can perform the matrix vector multiply operations corresponding to each layer, and then it can pass on the resulting activations to the next core and so on. So this is a true data flow architecture in that sense. And I want to point out that here the computational or the key attribute of the memory device that we use is the analog storage capability. You don't care for anything else. So the only thing you have to do is you have to map that synaptic weight that you obtained through your training process in software, and you have to map it into an equivalent analog conductance value on the device. So the only property that you are interested in is the analog storage capability. And how do we do this mapping? So we use what we call an iterative programming. So each, when you try to map a synaptic weight to a target conductance value, we try to use a feedback loop to achieve that target conductance value. So you program the device, you check for the error, you reprogram it, and so on and so forth. By using this iterative programming, we can try to get as close to the target conductance value as possible. And since it's an analog storage device, conceptually you can reach a certain conductance band. But because of all the non-idealities, because of the conductance variations and the drift and so on, in reality, we would end up obtaining a distribution of conductance values as shown here. So here, these are, so on a large array of devices, if you now program them to 32 representative states, this is kind of the distribution that you get. So note that, if there was no non-ideality, then you probably would have got a brick wall, right? You would have got exactly the 32 values that you decide, but in reality, you get always a distribution around that target conductance value that you're looking at. So this is one of the challenges we need to deal with, right? And this is what I will show next. Right. So because of the inaccuracy, and this, the distribution of conductance values that you reach, and again, this another plot which shows, the standard deviation of the conductance value as a function of the target conductance value. So you see that again, there is a distribution about the target conductance that you are aiming to achieve. Because of this, if you now train the network in floating point conventional manner, using TensorFlow or PyTorch or whatever, you bring in the weights and you map them into the PCM devices, there'll be a significant drop in accuracy. So you take an accuracy hit. Because of that, you need to do a custom training approach. So the idea here is to inject noise during the training process to make the hardware robust against these conductance variations, right? So while training itself, you kind of feed in noise during the process so that you are now robust against these variations in the conductance values. And this works beautifully. And what you see is that if you do this custom training approach, then you can kind of recover the lost accuracy. So this is what you get after this custom training and then mapping it into PCM devices. And then you can see that, okay, you recover the lost accuracy, and now you can achieve ISO accuracy. So you're just getting the training process get used to the inaccuracies that are there when you are running the inference hardware. So that's the essential idea here. So we performed a large-scale inference experiment to prove that this custom training approach works. As I say, the proof is in the pudding. So the weights corresponding to ResNet32 used to classify images in the CIFAR-10 dataset are mapped to PCM devices in this case. Each weight is represented by 2 PCM devices organized in a differential configuration. And why? Because conductances can only be positive, so you need 2 of them to represent both positive and negative numbers. And what you immediately see is that with a custom training approach, we can actually reach the baseline accuracy. So these blue dots here, these are the experimental measurements, and you see that you are able to achieve the floating point accuracy. There is a caveat though. There is this temporal degradation in accuracy arising from conductance drift. This has to be dealt with, but this can be partially compensated because the drift is evolving in time, and this has to be compensated through techniques. And what we show in this particular paper is that we can actually achieve accuracies well over 90% for a significant period of time, in spite of the conductance variations. And so I'd also like to discuss some aspects related to the system integration. So compared to all digital implementations, in-memory computing is particularly amenable to highly pipelined data flows that make use of the physically instantiated neurons and synapses. So here, for example, you can see a bunch of in-memory compute cores, connected together through a communication fabric. So hence, providing a communication fabric that can efficiently move activations from one computational memory unit to another is going to be critical for the success of this. So this is one work that we did in the context of convolutional neural networks, CNNs. Let's now first look at CNN architectures. So if you look at the CNN architectures, the key distinguishing feature is their connectivity. So first, from the origins of image classification to their rise in popularity in 2012, the networks used to feature a simple feed-forward connectivity. So that's what is shown here. And subsequently, in 2014, inception architectures introduced inception modules in which multiple layers within one inception block would process the same feature maps, and their resulting activations would be concatenated together. And in 2015, you had the residual connections as a solution to the vanishing gradient problem. And in 2016, a principle similar to that in inception blocks yielded this densely connected layers, so the DenseNet, right? In which a set of subsequent layers are fully connected with each other, concatenating their feature maps. So since then, the CNN architectural innovations have kind of stabilized. So what we did is we found that we can have a consolidated graph representation of all these state-of-the-art CNNs, where the vertices represent the convolution layers and the edges represent the activations. So you can create like this graph representation, let's call it like C. Now, it's possible to obtain, so what we also did is we proposed a 5-parallel prism topology as the basis for a communication fabric, and this one we denote by, say, F. So this is our F, and you have your C here. Now, it can be shown that there exists an injective homomorphism from C to F, and this is really nice because then, which means that we can execute any state-of-the-art convolutional neural networks in a pipelined fashion if we have a computing fabric which is based on this 5-parallel prism topology. So that's really interesting. So it's a nice way to design a communication fabric based on a graph homomorphism verification process. So here is an example of mapping ResNet32 on an array of computational memory cores that is interconnected using the 5-parallel prism communication fabric. The active links in this implementation verify the homomorphism as we described earlier. And each compute memory core, if you look at it, it has a modest digital processing capability like performing scaling, ReLU activation, etc. And its input and output memory. So this is what it has. So if you look at, so each compute core has these this is what it has. Now each core stores the weights corresponding to each convolution layer. The input memory stores the pixel neighborhood required for the convolution, and the result of the dot product computation is stored in the output memory. So if you do that, we can calculate the throughput, and that's almost 40,000 images per second, which is actually quite impressive given the state of the art. So this really shows the power of having a powerful communication fabric when you want to implement in-memory computing. When building new hardware for computing, one thing we realize almost immediately is that it is as much a software story as a hardware story. It is essential to develop a software stack that can compile a neural network model into operators suitable for the accelerator. The software stack is responsible to compile the model into optimized operations and routing and to orchestrate the data movement to and from the accelerator. So design of this software stack is a non-trivial task because the IMC accelerator is explicitly programmed as a data flow engine where the execution of the different neural network layers form a pipeline. So this is a very fertile area for research, and we expect a lot of work in this domain in the near future. Next, let's look at deep learning training. So here again, the untrained synaptic weights are mapped onto an array of in-memory compute cores. The matrix vector multiply operations corresponding to the forward propagation are performed in place. In a similar vein, during back propagation, the multiply operations with the transpose of the matrix is performed. And DL research shows that these two operations can be relatively imprecise. So it's perfectly okay to do the forward and the backward propagations in low precision. However, the gradient computation and accumulation, unfortunately, has to be in higher precision. So we do that part in a high precision digital unit. And so we accumulate the weight updates, and whenever this accumulated weight update is large enough, then what we do is we apply accumulative pulses to the corresponding devices blindly without reading back the conductance. So essentially, it's almost like you start with this network, which is encoded onto in-memory compute cores, and then you're kind of nudging it back and forth till they converge and to the optimal solution. And these synaptic weight updates are going to be very sparse now because you're doing the accumulation in the digital domain, right? So another big advantage, so that you don't have to program the devices that often, which typically is more expensive than performing the matrix vector multiplications themselves. So this is the so-called mixed precision deep learning training approach that we have been working on quite a bit in Zurich. And I want to point out that this is in this particular application, you see that we are exploiting now this accumulative behavior that we talked about, right? By we are nudging the weights back and forth by exploiting this accumulative behavior. So the mixed precision training approach works remarkably well in spite of all these non-idealities. And here's an experimental result showing that, where we implemented a 2-layer perceptron for Hamilton deep classification, all in place change memory devices, all the synapses are stored there, and all the training is done using that. And so you can see now here a comparison between what the software training gives you and what the hardware training or what the in-memory computing based training does. And what is really remarkable is that after you train and you reach a certain classification accuracy, you can actually leave it there and it will be inferring thereafter for a long period of time, in spite of, again, all the conductance drift and all the variations that we have in a real in-memory computing hardware. So it's really, really promising. In fact, this hardware that we trained on is actually available on the cloud for people to look at. So there is, if you go to this site, you can actually run a demo based on that hardware. It was trained like I believe like a year or two before, and it's still inferring, sitting there and inferring without any significant loss in classification accuracy. So it'd be great if some of you could just go there and try out. There's a lot more information on the website about how the whole thing works. It'll also be pretty interesting to read and try to figure out how it all works.
So what we have is essentially a device that does both memory and computing right at the location where the data is. So basically what this demo is about is we have hooked up the chip through the cloud. So the chip is located in the Zurich lab, and now it is connected through the cloud, and we can write our own digits and send it to the chip and see whether it gets actually recognized. So the chip was trained 9 months ago on the MNIST dataset. It is a 2-layer perceptron here, and now we can just use it for inference and see whether we write our digits, whether they will be classified correctly. I'll just do this, and then I'm sending the data to Zurich, and hopefully it will get recognized. As you can see, it works. And then here, what we will see in the visualization is basically the current that was flowing in the phase change memory devices when we input the data and it did the neural network classification.
Right. So the question is, okay, it works great for simple networks like an MLP doing MNIST classification, but how about larger networks? So we also worked quite a bit on that. So we could show that this concept indeed extends to much larger networks using very accurate behavioral models of the PCM devices, because we don't have such large arrays yet. So for example, here is a result on a relatively large convolutional neural network. And a surprising find is that in this case, we could also get a better generalization, right? Due to the noise which is coming from the devices, it's actually helping you generalize better. It's getting you improve the test accuracy on top of what you get typically from software. And since then, we have shown that this mixed precision training approach is applicable to other types of networks, such as LSTMs and GANs, generative adversarial networks, which, as you know, is notoriously hard to train even in software. So it's quite promising that it looks like we can do this in-memory training in a very, very, very effective manner without losing significant accuracy. So the mixed precision training approach is likely to yield software equivalent accuracies, and it's very promising. So that it's quite well established by now. However, analog in-memory computing is employed only for the forward and backward propagation stages and for the occasional weight updates that we do. The gradients are still computed and accumulated in high precision in the digital domain. So because of that, there are more ambitious approaches where the gradient computation accumulation is also performed in memory. I will not go into this in more detail, but there are some very good references that you could probably look into to understand more about it and how we could potentially develop this side of the things. So a third application domain for in-memory computing in deep learning is spiking neural networks. So if you look at a conventional deep neural network as shown here on top here, the neurons are static nonlinear functions. The synapses are scalar multiplier units, and information is transmitted as floating point numbers. Whereas in the more biologically plausible spiking neural networks, it's kind of like how our brain computes. Neurons and synapses are dynamic entities. Information is encoded in terms of time and transmitted by spikes. And SNNs are synchronous, and they do not operate on a global common clock. So much of the, so in that sense, it's quite, there are similarities, but there's also a lot of difference between how biological neural networks work and how the conventional neural networks are. And hence, much of the recent research effort is in trying to prove the computational efficacy of spiking neural networks compared to the conventional artificial neural networks. So essentially, we are trying to figure out if we can tap into the event-driven nature of it to do efficient training, for example, and also to kind of make use of this additional dynamics that is on offer, right? So definitely you should be able to do something better given that neurons and synapses are dynamic entities, for example. But even if there is a computational efficacy for spiking neural networks, they are notoriously difficult to implement on conventional von Neumann machines. So there is this significant research effort towards building custom computers to run spiking neural networks. Again, I would strongly encourage you to read these papers listed at the bottom, where there's a lot more information on some differences of SNNs to conventional ANNs, and some of the the research efforts going on in that direction. So much of the effort in this space of developing custom hardware for SNNs is using conventional digital and sometimes analog CMOS technology For example, custom digital circuits can compute the neuronal and synaptic dynamics like it is in the case of IBM's TrueNord or Intel's Loihi. Some folks like the Institute of Neuroinformatics in ETH and University of Zurich, they are using the sub-threshold MOSFET characteristics to directly emulate the neuronal and synaptic dynamics. That's also a very interesting approach. So what we have shown in the last couple of years is that in-memory computing can also play a key role in this space. So there's a lot of work going on where people are trying to use in-memory computing to implement some of the neuronal and synaptic dynamics natively using the memory devices. And this is extremely promising again, because implementing spiking neural networks in a conventional computing system is going to be extremely inefficient. I would like to briefly touch upon stochastic computing as well. So if you look at the resistance switching in memoristic devices, going from 1 to 0, 0 to 1, it's intrinsically stochastic, with an ability to control the stochasticity via the voltage and duration of write pulses. So this stochasticity, in turn, can be exploited for generating true random numbers, and then we can also use that to, for example, implement Bayesian probabilistic inference engines, or we can also use this stochasticity to have stochastically firing neurons and even physically unclonable functions. So you're kind of exploiting this intrinsic stochasticity in a very positive manner in many of these applications. I don't know if you know about it, but this physically unclonable function is a physical system that maps an input digital word to an output through a secret key that depends on an intrinsically stochastic property of the system. So you need that thing. That is one of the key attributes. So you can think of, for example, the memoristic crossbar arrays. They can be used to generate that physically unclonable function. The broad distribution of resistance values, as well as the current sneak paths that are formed, can be exploited to obtain a large set of challenge response pairs. And it'd be almost impossible to clone it. That's the beauty of it, right? Because it's not a pseudo random thing. It's a true random behavior. So this brings us to the last part of the lecture. So where we just talk about some of the more exotic research topics out there. So one of the key challenges of in-memory computing is increasing the computational precision, right? In particular, for the arithmetic primitive, it's a big problem, right? Whether you get 4-bit precision or 8-bit precision can mean a big difference. So the conductance variations, such as the drift and noise, severely limit the achievable precision in primitives such as matrix vector multiplication. So that is one thing that we need to deal with. And also we notice that the nonlinear and the stochastic accumulative behavior is detrimental for applications such as deep learning training, where you want to update the weights in a precise manner. So fortunately, there are some very interesting concepts in the horizon, and one of them is the so-called projected memory concept. So a projected phase change memory device is a slightly modified phase change memory device that exploits the IV characteristics of phase change materials to achieve very low conductance variations when used for analog storage. So it's an evolving memory device concept. We first proposed it like over 5 years back, and it's a very elegant way of trying to minimize or increase the computational precision of phase change memory devices. In fact, a couple of years back, we had an IEDM highlight paper where we experimentally demonstrated that the precision of this novel projected phase change memory device is comparable with 8-bit fixed point precision, which is actually a significant advancement over the state of the art. And although the precision is comparable, the devices can perform scalar multiplications using 33 times less power than conventional 8-bit digital multiplications. So that's quite impressive. So to deal with the non-ideal accumulative behavior, one of the best approaches is to use synaptic units with more than one memory device. So for example, you can have, in a multi-memoristic synapse for deep learning, the synaptic weight can be represented by in this case, for example, it's like 3 devices are collectively contributing to a single synapse. And this is kind of possible. Why? Because these memory devices, they can scale to very small dimensions. So you can actually have a pretty high density compute array, even with multiple devices constituting a single synapse. And what you immediately see is that we can achieve increased dynamic range, extended linear behavior, and reduced stochasticity if you have this approach. But of course, one of the key challenges in such an architecture is the device selection during writing, because you have many more devices per synapse, so you need to have some clever ways of arbitrating. And there's a lot of opportunity for innovation here. And in fact, one in this paper describes some of these approaches some of these very elegant approaches on how to deal with this problem of selecting devices in a multi-memristive synapse architecture. So let's go. This is my last set of slides. Let's just go a bit more exotic. So there could be one question, okay, is there a photonic counterpart to in-memory computing? Because what we talked about is based on electronic devices. So a couple of years back, a photonic memory device was proposed based on phase change materials again. So the idea is to have a phase change memory segment on top of a nanophotonic waveguide. Now the information is stored in the phase configuration of the segments, very much like the electrical one, but in this case, again, you store it in terms of the phase configuration. But both the reading and writing can be performed via ultra short optical pulses instead of electrical pulses. During write, the evanescent coupling and subsequent heating can be used to alter the phase configuration of the phase change material. The phase change material configuration in turn affects the optical absorption. So this information now can be deciphered by monitoring the optical transmission when a low energy optical read pulse is applied. So it's almost like very analogous to how electronic phase change memory works, but it's just that you read and write with optics instead. And instead of changing the electrical resistance, we are changing the optical transmission, right? So that's what is changing here. And indeed, we can actually have analog conductance states. So these devices can store a continuum of transmitted levels with clever choice of device geometry, pulse shapes, etc. You can tune it in a very nice manner. Last year, we published a paper where we took one of these optical memory devices and we performed scalar multiplication using it. So you could do a very similar thing like what we do in electrical memory. So in this case, you code one of the operands in terms of the optical transmission, and then you modulate the input pulse amplitude, in this case, optical pulse amplitude, and then you can perform the scalar multiplication. And one of the big advantages that we foresaw in that work is that unlike electronic in-memory computing, here we can actually exploit the inherent wavelength division multiplexing capability in the case of photonics, right? So which means that you can use the same block to perform parallel computations on multiple operands at the same time. So more recently, we extended this concept and we built a photonic tensor core, which have multiple of these photonic memory elements now organized in a crossbar configuration, again, very similar to how it is in the electrical domain. And this photonic processor implements an on-chip matrix multiplication and is capable of performing now parallel multiply accumulate operations using multiple wavelengths derived from a photonic chip-based optical frequency comb, right? These are some of the details. So you can perform multiple MVMs same time. And there is one operation that you all know where you need to perform multiple MVMs at the same time is the convolution. So it would have been nice to do it at the same time, right? Because you're taking a convolution kernel and you're sliding along an image, for example. And so what we thought is, okay, why not we try that out? So why can't we do all these MVM operations associated with convolution operations in a single time step? And that's what we did here. So we performed that whole convolution operation in a single time step. So it's a remarkable breakthrough in many respects. It's also quite exotic in that sense, and really pushing the frontiers of how we do computing going forward. Okay, that brings me to the summary of the lecture. So in-memory computing is this emerging non-fundamental computing paradigm where the physical attributes of memory devices are exploited to compute in place. Now, we can realize several logical and arithmetic primitives using both charge-based as well as resistance-based memory devices. Non-volatile binary storage, analog storage, and accumulative behavior are the key physical attributes of these memory devices when we try to implement various computational primitives. And we saw that, especially in the context of phase change memory, which is one of the prototypical resistance-based memory devices. So thereafter, we looked at a whole bunch of applications that are enabled by in-memory computing, spanning high precision scientific computing all the way to stochastic computing that kind of relies on imprecision. So first we looked at database query and hyperdimensional computing. These are two examples where the only requirement you have is non-volatile binary storage, right? They are dependent on in-memory logic operations based on devices that can provide you this non-volatile binary storage capability. So in the context of scientific computing, we realized that high precision is important, which means that we need to have ways to get there. And there are two essentially key ideas floating around. One of them is bit slicing, and the other one is mixed precision in-memory computing. So with these two, it is possible that we can still address problems in that domain which require very high computational precision. So thereafter, we looked at some of the applications where maybe the computational precision is not paramount. You are okay with approximate solutions. So that is why they're particularly interesting in that domain of signal processing and optimization. And we also saw a couple of examples there where in-memory computing could be used for it. So then we devoted quite some time to deep learning. In the space of deep learning inference, we talked about this custom noise injective training approaches, which is kind of needed to achieve that software equivalent accuracies when you map the synaptic weights into this hardware. Then we talked about the mixed precision training approach, where again, to achieve software equivalent classification accuracies, we have to employ this mixed precision approach, whereby we perform the forward, backward propagation steps and the periodic or the occasional updates of the weights in the analog domain using in-memory computing, but we still need to compute the gradients and accumulate them in high precision. And finally, we looked at some of the more exotic topics, which are geared towards, improving the computational precision as well as making it much faster and more parallel. So we talked about the projected memory and the photonic in-memory computing. So this lecture was mostly based on this recent invited review article that we wrote in Nature Nanotechnology. I would encourage all of you to read this article for more details and for further references. So naturally, given the time constraints, I couldn't touch upon all the topics here, so it'll be very helpful to read this and get further insights. I would also like to introduce you to this new toolkit that we have open source. It's called the Analog AI Hardware Acceleration Toolkit. So what you realize that when you're exploring new disruptive computing paradigms, such as in-memory computing, it's essential to have a large collaborative effort. So it's impossible for one group or one company alone to address all the challenges, as you saw, from the device level all the way to the software stack. So hence this year, we decided to open source one of our simulators that we use to establish software equivalent training and inference of deep neural networks. So this is a toolkit with which we develop some of the algorithms that gets us ISO accuracy. So it'll be really great if some of you could get involved in this effort as well and contribute to this open source project and make it a success. Now, coming to the acknowledgements, much of the work presented here was done by my team in the in-memory computing group. I would also like to thank my colleagues from the worldwide labs of IBM, in particular the IBM AI Hardware Center. It's a collaborative research hub headquartered in Albany, New York. I would also like to thank several academic collaborators, including some from ETH Zurich. I would also like to thank the European Research Council, the Horizon 2020, and the Swiss National Science Foundation for their generous support over the years. So with that, I conclude, and I'd be glad to take questions.
Thank you very much, Abu, for the very nice lecture. I think you answered a lot of questions on chat I was following. Are there any other questions for Abu?
Thank you, Onur.
I think this is a good opportunity to ask some questions. So maybe I'll ask a couple of questions if you don't mind. So I think this is all very exciting, clearly, and I like everything you described. The photonic thing, photonic in-memory computing is really interesting to me also. Can you comment a little bit more on that? Because I think you have some prototypes, right?
Right, yeah. So, I mean, the photonic one was a collaborative work with University of Minster and Oxford. So we are part of the EU project. Right, I mean, so what kind of started off that work was this in-memory computing paper that we wrote last year, where we showed scalar multiplication using this photonic memory. But we kind of speculated that, you know, because of the wavelength division multiplexing capability, that we should be able to kind of parallelize operations, right, which you cannot do in electrical domain. But then, yeah, so this year, or in fact, I mean, it already started last year, but yeah, I mean, this year is when we got all the results, right? You know, we could actually build like a true crossbar using that concept. And then also got these frequency combs from EPFL. So Tobias Kippenberg, he has this instrument there. So we got that, and then we combined with the crossbar, and we could show this one full convolution in a single time step, right? Which I think will be very difficult to beat with electronics, because, you know, as you know, like when you do convolutions, you're multiplying with the same kernel, multiple, you're just sliding through the image. So all that sliding is done in one time step, right? And it's really amazing, actually. So if you think about it, you can have such 200, I mean, you know, just by spacing the frequencies by, say, with 100 gigahertz, which is kind of very easy to do, you can actually have 200 parallel operations, all separate the frequency. So yeah, that's quite interesting, actually.
Yeah, that's great, actually. Yeah, I look forward to reading the paper that you mentioned from recently.
Yes.
I guess one other question I have related to that is, can you do everything optically? Meaning, do you need to convert once in a while between electronics and photonics?
Yeah, that is always the question that always comes up, right? Whether you know, you can do amazingly fast in the optical domain, and then at some point you suddenly have to convert to the electronic domain. And people always say, you know, that's the point where you kind of lose your advantage. Yeah, this is also something that we, I mean, you know, that we are also trying to kind of deal with, right? I mean, so for example, you can do these things for a single convolution operation, but if you want to cascade them or something, it gets a little bit more tricky. There are optical equivalents for simple activation functions. So technically, you can cascade to some extent, right? So you can think of like optical ReLU, which is, so to speak,
sure.
right? But if you want to do like some scaling or something, you know, it gets trickier, correct? Yeah, or more complicated activation functions, then it becomes a bit more difficult.
Yeah, I'm curious if you can do it reasonably well optically, then maybe you don't need to convert, right?
Correct. Yeah. And it could also be that we can have some signals which are natively optical, right? Coming from a sensor or something.
That's true.
Which could also be very interesting. But yeah, it almost looks like, you know, you do the computing so fast, and then you're kind of losing it in that intermediate steps, right?
Yeah, and the conversion part. Yeah. It is. Yeah, I think this is similar to the analog to digital conversion. I guess I could ask a similar question in the analog to digital conversion part.
Correct.
In the non-volatile memory based computations. I guess what's the state of the art in analog to digital conversion in that case? Is that as big of a problem today?
Yeah, I mean, clearly, you know, it is indeed one of the limiting things. And, you know, so what you see is that, so the kind of the rule of thumb is as follows, right? So if you can get your core to be beyond, like, say, 200, not even 200, even 100 TOPS per watt, right? Then you start getting dominated by your peripheral, like your ADCs and whatnot. So I also think that a lot of research has to go into that domain. So recently, from our group, we had proposed a very efficient ADC with a very small footprint. But I think there's also a lot of algorithmic tricks that we could play in that domain. And also it's not needed to have, at least for deep learning, inference in particular, there is no real need to have an ADC of more than 8-bit precision, because if you do it cleverly, the way you need to train accordingly, of course, right? You can, I think, work with something like 8-bit ADC, which is not too bad, right? As you know, things usually become worse when you start improving the bit precision, right?
Sure.
But yeah, so one thing that you've been looking at quite earnestly is current-based ADCs. So typically, people had moved to voltage-based, SAR ADCs for a while now. But for in-memory computing, I think it's, we can deal with some of the inaccuracies and non-idealities. So it looks like it's probably better to have a second look at current-based ADCs, which are, which are also much smaller, compact, and they also consume less energy. But you're right. But the moment you have a core which is at 100 TOPS per watt, which is still quite impressive, right? I mean, we haven't reached there yet, but then I think the ADCs will be the bottleneck and the communication, right? So let's also not forget the communication part. Right?
Sure.
So the activation communication will also become very, very important.
That makes sense.
Yeah.
I guess maybe I'll give opportunity for others to ask questions also. Anybody else? Yeah, I think there's one question. Is that new? Yeah. In-memory
in-memory computing with quantum. Yeah, that's an interesting question. But as you know, right, I mean, in-memory computing is very classical, right? There's nothing, you can just do it at room temperature, and so it's more comparable to conventional computing systems. Quantum is a different beast. I mean, it's definitely meant for certain specific workloads, right? Yeah, I don't know if there's like a real one-on-one comparison. IBM, for example, is invested in both of them for different reasons, right? I mean, we have this IBM AI Hardware Center, which is kind of pushing forward with all the innovative hardware for AI, which is based on both digital as well as analog computing. And quantum is another big part of the puzzle, right? Which is kind of geared towards mostly other types of applications, as you know. So I don't think it's like a exclusive answer here. I mean, I think both of them will coexist. I mean, in-memory computing, you're likely to see them in your mobile phones or on end devices, whereas quantum computers probably will reside in the cloud, right? Just because you need all this controlled environment and so on. So I think they will both be around, but will be deployed in different settings, correct? So this is the kind of the thinking here. I know that Onur is heavily invested on, for example, this gene sequencing kind of things. I think in-memory computing is perfect for that kind of applications, right? I mean, where you have edge devices or edge servers computing some of those things. Yeah, but quantum computing won't be for that, right? It'll be mostly for the cloud applications.
Yeah, I think, I probably agree with that. Although I maybe I don't know how to use quantum computing for gene sequencing. Also, that's also possible.
Right, but still, I mean, physically, I don't see unless people come up with some very good qubits over the next years, I don't see a reason. I don't see a reason why they would be integrated on the end device, right?
Sure. Yeah, in terms of the scalability of
the scalability
currently, certainly there's no match. Yes.
Really looking at, I mean, a big part of a mandate is to really look out like a 5 to 10 year horizon and not just the immediate, the next year, so to speak. But having said that, there are different types of projects in our lab, right, which are a bit more near term. In some cases, it's like something really long term. There are even people in IBM Zurich who are imaging molecules and and trying to figure out what happens like after maybe how a computer looks like maybe 30 years from now. So there's a wide spectrum of research going on. In my group, I would say it is more in this 5 to 10 year regime that we are mostly targeting. And we are also heavily involved with this IBM AI Hardware Center, which is kind of like a research hub with many partners, some of them even external. And we are kind of looking at building these prototypes, right? In fact, as you notice, some of the prototypes that you build, I mean, it's very difficult to get it done like in a small group setting, right? So we really need a lot of collaborators. And just think about it, you need to build a chip in a very advanced CMOS technology node, first of all, so you need a good foundry. And then you need someone to integrate these exotic memory devices on that CMOS chip. And then, you of course need all the characterization facilities and so on and so forth. It's definitely something that we have to, we are approaching from a very collaborative manner. And also, there are two parts of it. So one of them is the basic device physics, the circuits, the low-level stuff. Then there's a lot of work going on in the algorithmic stuff, right? Because I think going forward, there'll be a lot of algorithm device architecture co-design, right? I think Onur, has belabored this point probably many times in your course. That is probably where we are going towards. I mean, these things have to coexist. Like I showed the example of the CNN acceleration, right? If you just do like the individual convolution operation very fast, that doesn't mean anything. You still need to move the activations very fast, and you need this efficient pipelining in a deep network. And that is where you get your gains, right? So you really have to think through how you schedule the operations, what kind of communication fabric you provide. For example, if you give a crappy communication fabric, then you cannot do this pipelining, right? Because you have residual connections. You need to move the activation from, say, core 1 to, say, core 4, right? So you need to think through all this stuff. And somehow, I guess there's a lot of work going on in our group where people are thinking of these algorithmic system level co-design, right? So there are different dimensions to it. So there are basic device research, there is circuit level work, we build prototypes and systems, and then there are people who are looking at the algorithms and to a lesser extent the software. This is one area where we want to grow a bit more, but this is kind of the way in which our group is set up. I think there were a bit more. Yeah, for photonic computing, is it possible to other operations beyond multiplication? You could still do the accumulation in photonics too, because accumulation is mostly because you are just progressively crystallizing the phase change material, right? And I don't know if it was very clear in the lecture, but when you need accumulation is when you have to change your synaptic weights. So you have a deep neural network, right? You have some weights. You want to either train it from scratch, or you want to kind of adjust it to your voice. Let's say you have a network, a pre-trained network, and then you want it to be matching with your voice, right, or your data set. So then you may need to do some retraining, right? And how you do retraining is by using this accumulation. So you keep on nudging the weights, without having to bring it to a processing unit, right? You're just applying a pulse and it moves back or forth, right? So you're kind of literally changing it in place. And this is an application this is a primitive that you can also implement in photonics. So you can also shoot pulses, one by one, and nudge the transmission of the phase change material. So this is again another primitive besides the multiplication that you can do. Again, it's very analogous, surprisingly analogous to electronic. I remember how we started this project. We were just having this meeting with one of the professors after a conference, and we were just discussing each other's work. I mean, he was talking about the photonic memory, and I was talking about electronic in-memory computing, and then we were like, "Come on, this is looks so similar, right?" So there was hardly a difference we could see, and then we just thought, why not just marry the two? So it's like whatever you do in the electronic domain, you kind of can do it with the photonic domain, right? So this is another, how to. I mean, I guess. I'm sure that probably Onur is more qualified to answer this than me. So what we have been looking at in Zurich in particular has been mostly an accelerator-centric approach, right? So you want to build a custom accelerator for certain workloads. So we have a lot of flexibility in terms of, so it's mostly a compiler question then, right? I mean, you want something to be compiled to that custom accelerator. But there's also some activity that we are doing right now with EPFL in particular, where also looking at how to incorporate these kind of in-memory compute cores in a general purpose computing system, right? And there it would be clearly it will be like extending the ISA of the processor and these kind of things, right? And then trying to incorporate the cores in that setting, which there's also some work already in that domain, but yeah, it'd also be interesting to see, how much beneficial that would be, right? Already, it won't be as efficient or as spectacular like an accelerator-centric approach where you build an accelerator for a CNN or whatever. But I still think there are a lot of workloads which can benefit even by that approach, right? where you start having a more general purpose computer, so to speak, and yeah, and then what kind of instructions do we need to introduce and so on. For the accelerator-centric approach, it's a little bit more easier in a sense. We kind of have like a blank sheet of paper to start from, right? And then we just build up on that. Whereas the other one might be a bit more tricky, I guess.
Cool. Yeah.
I don't know if you want to add something more on that.
No, I think that makes sense. Basically, if you, yeah, I think if you want to incorporate in a general purpose manner some sort of processing in or near memory, then there are a lot of system level issues to tackle. We've discussed some of them in the course, but I think there's a lot to do over there for sure. Instructions, data allocators, memory allocators, how to do the data mapping, how to do the code scheduling, how to decide. Basically, there are a lot of interesting issues for sure.
Yes.
Yeah.
And but even though, having said that, even for an accelerator-centric setting like what we are doing, like for example the CNN accelerator, the compiler for that is non-trivial, right? Sure. Because you have numerous ways in which you could map a network onto that accelerator. And so we had this one paper in Eurosys, I believe it was beginning of this year, where we put forth some of the ideas on how you could go about it. We used like polyhedral compilation kind of ideas, where you could try to map in a more autonomous, clever manner, because most of the time you are kind of manually mapping, which is not the ideal thing to do, right? And sometimes you get like suboptimal solutions. So there's a lot of scope for, even in that setting, a lot of scope for like a compiler, like a real design of the compiler for that, right? I mean, it's non-trivial.
Yeah, absolutely, yeah. I agree. But you get a lot more benefit, of course, if you can not be general purpose and specialize your compiler for that special setting.
Yeah.
And that's the attractiveness, of course. Yeah. Okay. Any other questions? Maybe I'll ask my next question that if you don't mind. I guess I have two. One is, how big are the arrays that you're testing? What is the size of the arrays right now in your devices?
Correct. Yeah. So we have arrays of typically 256 by 256, 512 by 512, all the way up to 1024 by 1024. Okay. I believe at least, I mean, we haven't tested all of them. I believe the 1024 by 1024 should work. I mean, there's no reason why it shouldn't. But beyond that, I think it will probably start getting a bit more tricky. It just because of this IR drop, right? Because when you have long wires and also in advanced nodes, you'll have a lot of resistance. Then you probably have to make your devices more resistive so that that kind of masks the resistance of the wires. So in a sense, the resistance of the device has to dominate, right? That has to be the dominant resistance. So longer wires may create problems. But again, it's not clear if you want to go beyond that. It again depends on the application. If you're looking at say HPC problems like this linear solver, there's a big incentive in going to larger arrays. But if you're looking at deep learning, probably not, because many of the network layers can fit into one or two of the smaller size cores, and then you can do pipelining instead, right? So I think 512 by 512 is probably like a sweet spot as of now. And then try to improve the compute density, right? So that is where you can really push it, right? And unfortunately, it's also one of the disappointments for me right now, because technically these memory devices you can scale to nanoscale dimensions, right? So and if you look at like a 3D crosspoint chip or die, I mean, it is like gigabytes, right? So technically you could have an amazing compute density, but we haven't reached there yet in terms of making all the things work. But then you can have tons of synaptic weights on a single chip, or sitting there, right? I mean, this is something which would be really amazing going forward. But I don't know if there's any real merit in having, say, more than 1000 by 1000, 1024 by 1024. That's probably kind of the sweet spot. Or the upper bound even. Even if you can do it, I mean, so then you could just have multiple tiles, I suppose. If it is deep learning, of course, right? If it's some other application, maybe it's different.
Yeah, I guess it depends on the application, but deep learning, I probably agree.
Right.
I guess one related question is, what is the reliability characteristics of these devices in general? Like, deep learning clearly is very tolerant to errors that you get, so it's a great application
Correct. Yeah.
But would it work for really stringent applications that can tolerate no errors, for example?
I mean, yeah, that is true. I mean, see, the good thing about phase change memory in particular is that, you know, the read endurance is almost infinite, right?
Mm-hmm.
So if you are not programming it very often, reprogramming it, then I think it is quite good. You can use it, I mean, almost forever, right? If it's just inference. But if you want to modify it, it's like a billion. It's kind of the cycling
Mm-hmm.
cycling endurance of PCM. Which I think is probably fine for many applications. But I guess the biggest challenge in this domain would be, yeah, I mean, if you are using it for like scientific computing, like the example I gave of linear solver or something, then almost surely you have to have some tricks like mixed precision or the bit slicing approach, right? There's also some work I've seen on analog error correction, which is again one theoretical problem which I think might be interesting going forward, right? Because much of the error correction has been in the context of digital. So it would be interesting to see if we can already at least detect that a crossbar is behaving badly, right? And let alone correct. So that would be interesting. Again, I think very little work in that domain. I haven't seen much. I think I've seen like 1 or 2 papers max on that. But that could be interesting. Yeah, for deep learning, as you pointed out, it's remarkably robust. In fact, there are situations where, you know, you can have 5 or 10% of the devices faulty and you're still fine, right? Mm-hmm. And what is really cool is the in-device training, like the one that I showed, the mixed precision training, mm-hmm. Where that robustness is even more, because as you train in the device, it kind of adapts to that error, right? Mm-hmm. So suppose you have a bunch of devices broken or in crazy places, then that chip, it's sort of like our brain, right? It kind of mm-hmm. works around it. Sure. Whereas for inference, where you want to program outside and store the weights, you may need a bit more device level, you know, good behavior, right? Mm-hmm. I mean, it is still fine. You could always take that into account during your training process, but then it becomes mm-hmm. too cumbersome and not scalable. Ideally, you want your training scheme to be super simple, and then you should be able to map the weights, correct? You don't want a software which is like even more complicated than what you're doing. So in a sense, you could probably adapt to that, but you don't have to, right? I mean, it kind of is, it's already quite good in that sense. But I really like that in-place training where it's amazing how robust it is. I mean, you can throw anything at it and the guy kind of learns around it.
Yeah, that makes sense. Thanks.
Yeah.
Yeah, I think it's a good direction to explore analog error correction mechanisms. I agree with you that.
Yeah, that might be quite interesting. Yeah, I think there could be some good ideas there, I think, yes.
Yeah, and they could be generally applicable.
Yeah.
I could keep on asking questions, but maybe some other people should chime in. Are there other questions?
Maybe I can follow up on this question. So we have this endurance problem with phase change memory. And so are there any physical solutions to improve endurance? So despite smart remapping or error code correction or?
Yeah, right. So, you know, the source of endurance problem is coming because, you know, each time you are melting and quenching the phase change material, right, you are kind of moving atoms, right? And what happens is that because of the bias voltage, because when you're writing, you're applying a voltage pulse, which means that there is you know, the atoms have very high mobility, right? They're molten, and then you have a field across them. So it kind of pulls the atoms slightly apart. So suppose you have like a germanium antimony telluride or something, then you'll say that the germanium atoms will decide to slightly move in one direction as opposed to the tellurium atoms, right? So this is what happens. So then when you kind of repeatedly do the cycling, then they kind of move away from each other, and some point it's not GST anymore, because germanium will be in one corner and tellurium will be in the other corner. And this creates voids, and, you know, then the PCM kind of dies. So one approach that we tried to circumvent is to go and explore single elemental phase change materials. So this is one of the papers that we had in 2018, I believe, in Nature. It was actually on the cover of Nature Materials, where we showed that even a simple antimony, right, a single element antimony can act as a phase change material. But the catch is that you need to go thinner than 3 nanometers to be stable in room temperature. So if you make it extremely tiny, then you can have a single element which is acting as a phase change material. So in this case, ideally, it should switch forever because you don't have this problem of atoms pulling apart, right? Because it's a single element.
Oh, I see. All right.
Yeah, so this is one thing that we have been looking at, but definitely this means that we need to fabricate devices which are confined to like 3 nanometers or less, which is still a challenge when it comes to really incorporating into a process, right? Because we are currently we are building these experimental devices. At least the one that we fabricated for the Nature Materials paper was using e-beam lithography, which is not possible in the fab. So that is kind of one approach that we're looking at from a physics point of view.
Okay, and what about this photonic in-memory computing? So do you have the same effects there? I mean, you don't heat
I
up.
suspect it's a little bit different there because there's no field, right? So it could manifest differently, but I haven't really looked at it. I need to discuss with Oxford guys on whether they have measured the endurance. But I suspect that we should also see some effects there, even though it doesn't have a field, right? But there are still thermal gradients and all that. So anytime your atomic mobility is very high, bad things can happen, right? In fact, for me, having worked with PCM for almost more than 10 years, it's even a miracle that this thing works for almost 1 billion times, because you're literally it's a brutal way of doing things, right? You're just literally melting the material and you're quenching it.
I was also a bit surprised. That's why
it's just amazing that this thing works so reliably. In fact, we had one of the chips we fabricated where the CMOS failed before the PCM. It is funny. Of course, we are overdriving the CMOS circuitry, but on the other hand, I still found it surprising that it was the CMOS failing before the PCM, and that was kind of.
All right. Okay. Thank you very much.
Yeah, it's beautiful technology. I think I remember in the 2000s or so, a lot of people were very skeptical that this would work.
Yes.
And
there are still some problematic aspects of PCM. So one of them is the so-called threshold switching voltage, which is a bit annoying which means that you need a certain threshold voltage before you can switch the material. This kind of limits the ability to integrate on very advanced nodes, because then you need to provide that voltage through a transistor, right? So which is a little bit, or a transistor should be able to withstand that voltage. So this is kind of, again, one of those things which people are looking at. There are still some open problems, but you're right, Noor. I think it has really come of age, right? The technology, and people understand much of what is going on there.
Yeah. I mean, due to a lot of investment, of course, from many people, clearly.
Exactly, and compared to resistive RAM in particular, right? I mean, the physics is much better understood. So if you look at resistive RAM, every other week you see a new paper, right, on a new theory of how it works. Whereas in phase change memory, it's a bit more stable. In a sense, people now kind of know the basics, right, and how it works and so on.
Yeah.
It's also amazing.
Any other questions?
Hello, I have a question on the mixed precision. I found the concept very interesting because it's the first time I saw it this way, where you have a high precision unit for having feedback and a low precision unit for the computations. Can you comment on the trade-off we make here by having very good feedback versus having to repeat many times the computation?
Yeah, right. I mean, see, first of all, the iterative solver is always iterative, right? So, like if you want to solve like AX equal to B in a standard digital setting, like in an HPC setting, and if A matrix is huge, like 10,000 by 10,000, almost never you decompose you don't do the direct solution, right? So you never try to find, trying to invert the A matrix. You don't do that. So the iterative refinement itself is not new. That is something which you would do even in a digital setting. So what is new here, though, is that the that inexact solver you implement using IMC, right? So using in-memory computing. So that is a new part. And what you gain by that is that the number of iterations comes down drastically, where you have to do this high precision residual calculation. So if you look at the graph that I had on my presentation, you see that the number of times you have to do that, R is equal to X minus B, that operation, that one has come down by a factor of 5 or so. Okay.
Mm-hmm.
So it's not like, it's not that we have to do iteration because of in-memory computing. Iterative solver is what you would anyway use in these kind of large problems.
It's just getting faster because it's in-memory computing.
Exactly. In fact, you're reducing the number of high precision residual calculations or high precision AX operations you need to do because of the use of IMC.
Okay, I see. Thank you very much.
Welcome. So that's a very interesting question. So there are two things to it, right? So one of them is, so part of the reason why SNNs can be interesting is because it can provide the energy efficiency, right? So suppose you have trained an SNN and you can just implement it, you can just do the inference on it. Then you can make use of the sparsity. I mean, especially if the inputs are sparse, then you can kind of make use of that, and then you can have better efficiency, right? Because you're kind of event driven. So you only compute when a spike comes. So that gives you the efficiency. So that is the inference problem of SNN. And for the inference problem of SNNs, what you can do is you take an ANN, you can either convert into an SNN, or you can also train an SNN to get comparable accuracy like an ANN. So there are a lot of approaches which have come up in the last couple of years, including there's one from our own lab, which was published this year in Nature Machine Intelligence, where it was shown how to train like an SNN using standard ANN tools. So that means you can have a TensorFlow, with slight tweaks, by introducing a new unit, you can actually train a spiking neural network offline, and then you can map the weights for inference alone. So this is interesting, but for me, I think it is just part of the story, right? This efficiency coming from sparsity. This is definitely, I'm not demeaning that, it's definitely interesting, but I think the real power of SNN is going to be twofold. One of them is that you may be able to exploit the additional dynamics in the synapses, for example, to bring in some new computational benefits. So we have an arXiv paper right now showing that by having additional short-term plasticity, for example, you can solve certain problems better. Because just one example is, if you have an ANN which is trained to look at cats, right? It's great when it's looking at cats, but if a cat just hides behind a cupboard, then the ANN might fail, correct? But if because of this additional dynamics that you can introduce at the synaptic level, you are able to sometimes detect these kind of situations where your object that you're trying to detect is also changing in time. And so we have this nice algorithm which we developed. I mean, it's called short-term STDP. This paper is on arXiv, and it kind of shows that an SNN with short-term plasticity kind of has the optimal solution for that kind of a problem, where you have these kind of changing environments. So for me, this is the most fascinating area. And unfortunately, we are still not far there. I mean, people are looking at it, a few groups, but I think a lot more research has to go in there. So this is one advantage, right? The computational efficacy of SNNs, because it has this additional dynamics on top of ANNs. The other big reason why you probably want to do SNNs is because you can do on-chip training, right? Without backprop, because then you can use local learning rules like spike time dependent plasticity to train in a very local manner on chip in a very efficient manner, which, as you know, would be a huge benefit over ANNs because training consumes a lot of resources, right? But unfortunately, this on-chip learning is again at its very primitive stages, right? Because we can probably train like a one layer, but more layers, it's always challenging. There are a few approaches here and there, but it is still not fully there yet. But I would say that training offline and mapping it into an SNN is almost a solved problem now. So we can train, I mean, that part, the very first thing that I mentioned, when you want to use SNN just for inference, that is almost there. But the other two things where you want to use it for new computational benefits or for on-chip training, that is where we are still quite far away. but I think there'll be quite some work in that domain going forward. So you can actually read the couple of papers I had on SNNs as references. And also this, I forgot to attach this one, this archive paper where we showed this, we called it the, what do you call it again? The elastic clustering. So these three papers could be very good read to know more about, the status of SNN research right now.
If you could send me that paper, we can get it posted.
Sure, I
on the website.
I can send it. Yeah, sure.
Okay, thanks.
Yeah, so this is what I was also discussing with Onur a while back, right? So if you go too small in the course size, then your TOPS number will be less, right? Because you take you may have to take like a certain time no matter what, because you need to settle down in your voltage levels and all that stuff, right? So you want to perform a MAC-op, you want to perform an MVM, then it may, let's say it takes 100 nanoseconds. It could be faster too, but let's say it takes 100 nanoseconds. So if it is 64 by 64, or whether it is 1000 by 1024 by 1024, you take the same time. So your TOPS number will come down drastically if your crossbar size becomes small. And moreover, your overhead might be more, right? Because you're getting less TOPS, and then you have to do more, you still have your other periphery which you need for that one, right? So 64 by 64 is probably not very advantageous, but on the other hand, 1000 by 1004 may be an overkill, right? So for me, I think 512 by 512 is kind of like a sweet spot, especially if it's deep learning. That might be, it's still an open problem, and it again depends heavily on the applications, but I would say 512 by 512 is probably, that's just my feeling, that probably a sweet spot there.
I think we've got a lot of good questions though, either spoken or written.
Yes, really nice discussion, yes.
Yeah.
Maybe is IBM planning to bring one of these techniques to market? Or do you know, or is this yeah, I don't know. Can you answer this question? Or
sure, yeah, clearly,
I'm just curious if we. Okay.
Yeah, see, we do many things, right? Of course, we do bring some things to the market. Sometimes we license the technology to others. So there are many commercial avenues. AI acceleration for sure is a big, a big goal for IBM, right? So this is definitely, that's why we have this IBM AI Hardware Center, where we are looking at different concepts, right? Some of them may be shorter time horizon, some of them may be a bit longer, and so on and so forth. Yeah, so definitely our goal is, of course, to commercialize, but it may not be that IBM has a product. It could be that IBM makes it together with a partner. There are many avenues like that. So we have done it many times. For example, sometimes when you're doing something on memory, IBM is not necessarily a memory manufacturer, right? As you know, the memory manufacturers are the Microns and Toshiba and so on. So sometimes you work with them, and then you make sure that the product is in the market, and then use it in IBM systems. So you may not see like a product saying made in IBM or made by IBM or IBM inside, but but yeah, sometimes it comes in different flavors. Kind of like what we did with PCM, for example, right? We had a long PCM project, but doesn't mean that IBM has a PCM chip. But of course, some of our knowledge and know-how has gone into some of those.
Okay, I see. Yeah.
Might be kind of hidden at times.
All right. Okay, thank you for the answer.
So maybe I'll ask a very speculative question. The one that I usually get also when I talk about emerging technologies. So clearly PCM has made it out to the market. Do you foresee any other technology making it out into the market, at least in a more or less, let's say, general purpose way?
Yeah, so there is also resistive RAM in very niche markets, right? So there is this Crossbar and a couple of companies who are smallish chips.
Sure.
MRAM is another, I think, a very powerful candidate. I still think that MRAM, at least in the embedded space, I think it has a strong promise still, right? Samsung at least is heavily invested on that. Yeah, so I expect yeah, I expect all. I mean, I expect all of them to be commercialized. But initially, you see, I mean, maybe Onur, I think since you're following it quite well as well, right? I mean, initially, you know, all of us thought that there'll be this universal memory which will come and it will eat up everything. But it didn't happen, right? So in the end, it almost looks as if the different technologies are kind of taking up different parts of that universal memory story, right? So you have MRAM possibly replacing embedded DRAM, so more going into that, you know, the memory end of storage class memory, PCM kind of in the middle. Then you have ReRAM potentially could take up the storage end of the storage class memory. So it's kind of got fragmented a bit. So initially, everyone thought, oh, there's this one technology will come and you kind of swallow the whole space, right? But that SCM itself got split into many segments. Yeah, so in some sense, I would say PCM is probably the most advanced for sure, but I think MRAM and ReRAM could also have their own space in that SCM story that is developing. And another one to watch out for is ferroelectric RAM. I don't know if you have been following it much, but so that is making a comeback, not in terms of FeRAM, but in terms of the, you know, with the FET, ferroelectric FET, right? So where you have a transistor where you are, you know, you have this ferroelectric element there, right? I mean, this is kind of, so it's a non-volatile transistor, so to speak. That's also getting a lot of traction of late. That's I believe that's kind of the wild card among the lot. I mean, among the new technologies on top of PCM, ReRAM, and MRAM, because there's some very interesting results coming up. You know, looking very promising actually.
Yeah, I've seen some papers along that direction. And I think I agree with you in general. It's good to be optimistic in terms of technology because you never know where one could be used and what kind of breakthrough can come through, right?
Yeah, and the unfortunate thing, I mean, is that especially for technology, the time scale is so long that in the new world where it's app world, right? I mean, it's like or software world where you conceive a product and then you commercialize it like in I don't know, a few months, and then from, I mean, if you contrast that with like the technology space, like the time scales are so long that usually people lose, I mean, kind of lose patience, right? So I always say that hardware is not for the faint-hearted. I mean, it's really, if you look at PCM, yes, 2000 time frame, everyone started moving towards it, and it took like 20 years, right, from 2000s to the time when you could get something reasonable out. So this is kind of the time scales that we're looking at, and everyone is like impatient to see the thing. I mean, you know the history of Flash, right? I mean, how long it took before that became a big success. I mean, if you look at every technology like that, yeah. But I can see the impatience because software is much faster, and you see a lot of progress, and you're like getting so excited by it. But then sometimes you forget, okay, what brought us there, right? I mean, even if you look at deep learning, I mean, it's not because of the algorithms; they were already there in the 80s, right? It is essentially the computers and the memory and the technology which got us here, and people just forget that. I mean, and they just think, oh yeah, this is all because of algorithms, right? And we don't. But
I think
they kind of forget the hard work that went through to get us there. Which is kind of annoying sometimes.
No, I think it's good that you're talking about this because I cover some things related to this also in the course, and we discuss exactly what you mentioned. Hopefully, you're preaching to the choir here. The students here are well informed as opposed to.
Yeah. I mean, I think I can understand the computer architects can understand it better, but when you talk to software guys, it's like they're completely oblivious to this, right?
Yeah.
Why things take that long, and they're asking, okay, where is the hardware, right? I mean, it doesn't just pop up like that.
yeah, exactly. Yeah, I think that's where education should play a bigger role, frankly, because
yes, and also the cross interaction helps sometimes. Sometimes, especially when we are like talking with the compiler guys and the software stack guys, they kind of understand some of the intricacies, right? I mean, because they're just used to getting an interface and writing something on top of it, and when they see under the hood and this is what it is, then they have a better appreciation for the efforts that is going on below that, right? Yeah, I think it would really help to have more like interdisciplinary groups and environments where people get exposed to some of the like some of the lower level stuff, right?
Sure.
The basic physics as well.
Yeah, breaking the interface and understanding what's going on
correct.
underneath helps a lot for sure.
Yeah.
If you're writing an app and you don't care about how it's executed, you don't even know how it's executed, I think it's easy to dismiss the fact that there's been a lot of work that made it happen.
Correct. And many things, if you look at Flash, for example, like MLC or TLC Flash, I mean, the endurance is like 1,000 or something, right? And the system is just completely hiding all this stuff, right? I mean, you're working with an IBM Flash system, so something, you don't even see it, right, as a programmer. But then when you look deeper, you see all the ways in which you counter these unpleasant things, correct?
Yeah.
And so some of the questions about PCM with 1 billion endurance, that's a lot compared to Flash, right? It's like orders of magnitude more. And we are perfectly okay with, or we are so confident of our flash drive on our computers, but we don't trust PCM. I mean, that's kind of. Yeah.
I guess any other questions, comments? Any other comments you want to make, Abu?
No, I think I really enjoyed the discussions, and please, don't hesitate to email me. And hopefully after the COVID times also, you could probably, I mean, Onur, you especially have to come. I mean, you have to come to IBM and give a talk at some point. It's
been a while.
it's long due, yeah, exactly. And I think we should also probably work on some of the, I mean, I'm really looking forward to also collaborating with you on some of these topics. I think there's a lot of synergy from what I see, what you're publishing and what we're doing. So yeah, it'll be great, I think, to have some strong interaction, either within a project, a European project or whatever, or just bilaterally, right? I mean, it would be really nice.
Yeah, I agree. And I'd love to come and visit at some point. And thank you for spending the time with us for this.
No problem, yeah.
I think it was really informative and useful. It certainly gives a different perspective to the students.
Thank you.
I think that was very useful for sure. I learned a lot.
Thanks a lot. Yeah. So I think it'd have been much nicer to come in person and talk to all of you, but unfortunately, with the
sure.
COVID situation,
it's probably much safer not to do so.
Yes. And also wishing everyone a very happy holidays.
Okay, that's great. Yeah. Okay, well, if no one has a burning question left, I think some people are thanking you over the chat.
Thank you. Really appreciate that.
Cool. Yeah, thank you very much, Abu. We really appreciate it. Yeah, and we're going to close the session right now. Everyone have a great weekend.
Bye-bye.
And see you next week.